This video is the next in the series on the Control101 MATLAB toolbox, and here we're going to look at an app to support an understanding of PID auto-tuning. The community then has agreed on an outline structure for a Control101 course, and this MATLAB toolbox has been developed to support such a course. The reason is because MATLAB tools enable visualization and support tedious number crunching so students can focus on core concepts. Now this particular video is going to focus on one of the resources which is on auto-tuning of simple PID compensators, because these are very widely used in the community and quite important. And you'll see we've summarized what a PID compensator might look like in the yellow box. What's the context of auto-tuning then? So there are a large number of different tuning rules for PID compensators available in the literature, and they're all based on slightly different assumptions, though similar. It's not the purpose of this app to explain those tuning rules in detail, but rather to provide a framework where students can compare and contrast them efficiently, so they can look and say, oh, there's method A and method B. How do the behaviours vary depending on which method I choose? There's a lot more background and references provided in the manual file, which opens automatically when you run the app. So, what can users do? They can modify a modelling parameter. So that's what you do, and I will demonstrate that in a minute, and see what impact that modelling parameter has on the PID auto-tuning behaviours. And the whole idea is, because this is auto-tuned, all the calculations done by MATLAB in the background is pretty much instantaneous. So the user can, what if I change this? Oh, that happens. What if I change that? So and so happens. So, auto-tuning assumptions. So many popular PID auto-tuning methods approximate the model by a simple second-order system with a delay, a bit like the figure shown here. So you can see, in essence, the delay is this value L, K is the expected steady state, and then we sort of look at something roughly around the 63% line, and we might call that T, in essence, a time constant. So here's the key thing. The user has to make choices for these parameters. Where exactly are you going to put them? And the auto-tuning method takes these parameters and forms the control law. So the choice of T, L and K is not unique. It's not fixed. There's a certain amount of, well, L might be here, it might be there, because systems don't have a real delay in practice, they have an almost delay. So there is a bit of fuzziness in your choices, and that fuzziness will translate into the PID design, and you basically have to live with that. So here's an example of some of the auto-tuning rules. You can see here Ziegler-Nichols. The proportional depends on those three parameters. The integral depends on those parameters. So basically, this is how auto-tuning rules work. Now, I'm not going to give all the details in this video. They're available in the files if you download them and look at them. And just a warning, in practice, the derivative term is appropriately filtered to avoid derivative kick. So what does this auto-tuning app look like? It might seem quite busy, but we'll summarize it here briefly before we go and demonstrate it. You'll see first in this top yellow box, this is where you choose your system. So there's a number of pre-coded systems already there for you to choose from. Okay, next you need to choose your parameters L, T and K. So this is the thing that everything else depends upon. You have to make those choices, and you use these sliders. Now there's a few other boxes where you can make choices. Which control law are you interested in? Is it P? Is it PID? Which tuning rule are you interested in? And if you want to overlay several tuning rules at once, you can see you've got these buttons here. Green means I'm going to include this, red means I'm not. So it's fairly transparent which ones you want to do. And then in the final box at the bottom, you can also do a manually tuned PID of your choice. So let's go to a live demonstration and see what this app looks like. So here's the app. So essentially, I just open it. Oh, I'm going to have to make it slightly smaller to fit. There we go. So here's the app, and what you can see is I've got a particular system you'll notice it's down here. There's the system that I've currently got. Okay, and my first step is to estimate these parameters L, T and K, and at the moment you can see from these lines my estimates aren't very good. So let's try L. I'm going to try something like 0.2. Does that look sensible? So you can see this vertical line's moved. Do you think that pretty much approximates the sort of delay this system's got? It's a choice. You might say, oh no, I'm a bit happier with slightly bigger. There's not a right and wrong answer. There's a certain amount of variability here. You make the choice. Now what about this K, the steady state? You can see clearly that's wrong. It must be about 1.25, so let's change the steady state. And now you can see it's pretty much overlaying, so my steady estimate's about right. And then finally, I need to get T right to make sure that approximately I'm on 63%. Now in truth, that's not an exact calculation, as you'll see if you read all the references, but it's not far off. So let's try and move that T, keep reducing it, and now you can see it's roughly in the right place. So now I've got my L, my T and my K. And so what's going to happen next, so I've characterized the system, is I want to create the responses. So let's go straight to PID. So I'll select PID in this box and let's go create responses. And now you can see the sorts of responses we're getting. Now, here's an interesting point. Everything's gone flat. Why has it gone flat? What does that mean? Well, you'll notice in the caveat, it basically says that if the system is unstable, if it's closed loop unstable, you will get flat lines. So if something's gone wrong with my... Now, that's somewhat of a surprise. You're saying, well, I didn't really expect it to be closed loop unstable, but let's not panic initially. Let's see what happens if we try some of the other methods. So you can see these button ears. I can try some of the other methods. I'll just pick some at random. So you'll see they've now marked in green. And then if I put down all PID, and let's have a look. And what you can see is that for many of these PID tuning methods, the response is not too bad. But for this particular case, Ziegler-Nichols seems to be failing. And that's why you're getting a flat line. And that's informative in itself, because what you're seeing is when things fail and when they don't fail. And you're seeing here clearly the differences between the different tuning methods. If it's not clear why there are so many figures, you'll see the figures basically look at different sensitivities. So the top one, output response to target, top right, input response to target. This one in the middle, output response to output disturbance, output response to input disturbance, and so on. So you can see there are different sensitivities you might want to investigate, and that's why there's so many different plots. And so again, you can see you can change different control laws. I can say I just want to look at PI. So we can do all PI, and there are the responses there. So in essence, you're in charge. You can decide which compensators you want to compare. You can do your manual compensated one down the bottom if you want to add it. And you can go back and you can recharacterize your system if you think it's wrong. And then you can maybe do a different system. So here's a different system. That characterization's not quite right. Do the characterization and then have a look and see what's going on. That's just doing Amigo. Let's do all PID and so on. So hopefully it's fairly clear that the app allows you to investigate very quickly and efficiently different tuning rules and also the impact of the parameters that you can choose. So we've demonstrated how to run and use the PI tuning app in the Control101 toolbox. So this can be used in lectures if you want, or for student private study, to help students appreciate and relate their technical and analytical learning. And if you want more detail, they're in the manual. The manual will always open automatically when you run the file.